Welcome, everybody. This is GDG Cape Town's event for October, and we're tackling the topic of Rust. The title of our event is, Are We Rust Yet? So what we're about, we are GDG Cape Town. We're an official Google Developer Group chapter. We are self-organized and independent, but we are supported by Google and by local sponsors, and all our speakers and organizers are volunteers. So what this means for you is, if you would like to sponsor, or if you would like to speak, or if you have a topic you want to suggest, please contact us and tell us what you would like. So how can you get in contact with us? There's a chapter at this link showing on screen, and I'm sure Ahmed can post us a link in the chat as well. You can tweet us at GDG Cape Town. You can email us, gdgcapetown@gmail.com, or if you're on ZA Tech, you can find us at GDG Cape Town channel, or you can just ping any of the organizers. So you may ask, who are the organizers? Well, I'm an organizer, Sylvia is an organizer, George is an organizer, and Ahmed is an organizer. And you can find us all on either Twitter or on ZA Tech. As with all kinds of events like this, we do have a code of conduct, and you can find
Maya, can you hear me? I think you went mute at the code of conduct start. So let me quickly double check and see what's going on here. I see that Maya has disappeared, and I suspect it's because Stellenbosch is just being low chat now. So give us a few minutes for Maya to fire up her batteries and dial in again. And if that doesn't work, I'll take over from here. Maya, you're still muted.
Okay, falling back to the microphone. Okay, yes, it was load shedding. All right, where am I? So I was going to say that Duncan, the previous slide was the code of conduct, and this slide is our agenda tonight. So the first up on our agenda is Duncan. Duncan is my friend and colleague at Luno. He is also a Bitcoiner and a Rustacean, I believe is the technical term. And Duncan was going to tell us about the rusty dinosaur, and I'll let him do the explaining. But before we get there, as a tip, there is a Q&A tab in the chat bar. You can post your questions there. You can also at us if you want to come on stage, and Ahmed, our moderator, will make sure that we are managing the questions properly. So without further ado, I am handing over to Duncan. I'm going to add Duncan to the stream. I'm going to remove myself.
Thanks, Maya.
Can I add your slides? I can see your slides. I can hear you. And
Perfect.
with that, I'm leaving the stream.
Thanks, Maya. Let's hope the load shedding doesn't impact my talk too much, but yeah, that's something we have to deal with. So, hey everyone, you can just say hi in the comments. I can see your comments right now. Yeah, so I've named the talk The Rusty Dinosaur. We're actually talking about Dino, if no one got the hint. Yeah, so a lot of Dino is actually implemented in Rust. It's a JS runtime. So we're going to take a look at actually implementing a web API, one that doesn't yet exist in the specs, in Dino itself with Rust. So a little bit more about me is, as Maya mentioned, I'm a colleague of hers at Luno. So I do web stuff mostly. I've been using Rust for a while, kind of on and off, some WASM-specific stuff with Rust, which have been getting back into it in some open source contributions. You can find me on Twitter and GitHub. It's both at Dunkson. And then if you're feeling a little nerdy, here's my PGP fingerprint for my key. So if you want to send me encrypted mail, please do so. If you have any questions about the talk, please don't hesitate to contact me on Twitter as well. Okay, so maybe just a primer on what is Dino. So probably came on the scene about 3 years ago, but if you still haven't heard about it, it's a simple, modern, and secure runtime for JavaScript and TypeScript that uses V8 and is built in Rust. So TypeScript is supported out of the box, so it will pre-compile to JS and then run that JS. There are no project-specific dependencies, so this might seem a little weird if you're coming from like Node or actually any other NPM-managed JavaScript project. So there is no package JSON that you need to worry about or node modules that are specific to the project. Instead, Dino actually uses native ES module import syntax and to either import a local file in a project or from any other URL. These types of dependencies are then cached, and versioning is actually handled by semantic versioning within the URL string itself. The one nice thing about Dino as well is the Dino executable is actually distributed as a single executable. There's no other dependencies. It's all self-contained. And then the one thing that they sort of pride themselves in doing is always going the web standards route. So using web streams over like their own stream implementation, and yeah, just also helping push the web forward, which is really great. And it also has a compat mode flag, which enables compatibility with Node.js. So if you do have Node.js specific packages that you still want to be able to run with Dino, you can. This support isn't 100%, but it's getting better every day. If you do notice any issues when trying to use it, then you can always open an issue on the Dino project, and everyone's happy to help. All right, taking a look at a very small sort of focused view on the Dino architecture. There's obviously a lot more crates to this than what's displayed here. But so you could call this the anatomy of a rusty dinosaur. So it's some of the stuff we'll need to know a little bit more about for this talk. So the CLI crate is probably what you're most used to with Dino. So that's the actual single executable that you can pass subcommands to and actually run your JS files and TS files. So yeah, that's the actual Dino executable, and it provides all the user-facing APIs. So core is actually responsible for the creation of V8 context. So it implements all the V8 bindings between Rust for Dino, and it also implements the JS runtime. So the runtime crate exposes the main worker API. So in Dino, in each Dino program, there's one worker, and that would be, there's at least one worker, which would be the main worker, and then that can spawn other workers further down the line. Yeah, and then that API also encapsulates the JS runtime. And then we have a bunch of extension crates. We'll be looking at extension web for our web API, but there's a lot. It's like crypto for web crypto APIs for digests and subtle crypto and things like that. yeah, so it contains JS and the Rust ops for that functionality for the APIs. So a quick look at the JS runtime struct. So this is defined within Dino. Every runtime is associated with a V8 isolate. When we talk about a V8 isolate, it's an instance in V8 with its own heap and garbage collector. And when we talk about an owned isolate, that has implemented drops, so that when it goes out of scope, so the owned isolate actually gets disposed when it goes out of scope. And then we have a snapshot creator. So this is just a helper to take a snapshot of the V8 heap during the build process for the runtime. And then extensions. This is probably quite important for this talk. Yeah, it's just it contains the JS files and the Rust ops that adds functionality for the different web APIs to the JS runtime. And then I've just removed a few of the fields that we're not going to go into right now. They're not super important. So then in Dino CLI build, this happens when you actually build the CLI crate. We create a new JS runtime. We pass it runtime options. Will snapshot is the most important here, and that's basically prepares the JS runtime and its own V8 isolate to be snapshot. And snapshotting is basically just a process of serializing the V8 heap into a binary format that we can include in the Dino executable itself, and that can be used to recreate the V8 heap at a later time. So it allows quick startup times. You don't need to initialize an isolate from scratch each time. Yeah, so when the Dino CLI is shipped to you, it already contains this snapshot to get going within it. So now if we just take a look further down in build.rs create snapshot, then we'll just call the snapshot method on JS runtime. We'll get a slice from that, and then we just write that to the snapshot path that will be used later on in the build process to include in the executable. All right, and down to our web API. So this is what we're actually going to be implementing in Dino. It doesn't exist in Dino currently. It's not part of the proposals process. It was actually, it's actually in a draft proposed by one of the Dino core maintainers. And it's similar to text encoder, except we're not working with text encoding. So you might have come across a use case where you want to basically have a binary encoder or decoder. I'll explain the one use case or the one use that I needed for it. So here we can take in a Uint8 array, maybe from a file, and we pass it to crypto.subtle digest. We want to get the SHA-256 hash of that file. So we get the digest, but the digest byte is actually still a Uint8 array. We want to get a string representation in hexadecimal. So we can create a new binary encoder. We pass the encoding hex there, and then we can encode the digest bytes. And then digest itself will be a string representation. So it will be the normal hexadecimal SHA-256 that you're used to seeing. And then on the decoder side, so this is one use case in a recent Luno hackathon. We were implementing WebAuthn, and we'd get a base 64 encoded challenge from backend, so that it'd send in a response. And then in order to use it in the WebAuthn API on the front end, we actually need to convert that to a Uint8 array. And obviously, you get your standard functions that you can just take a peek at on Stack Overflow and see, how to convert between base 64 and Uint8 arrays. But I was kind of disappointed to find out the web didn't have, something lying around as a web API. And this sort of solves that problem where you create a new binary decoder. We specify the base 64 encoding, and then we just decode the string, the FIDO challenge string, and then we'll actually challenge data will then just be a Uint8 array out. So that's what we're doing today. We're actually going to focus just on binary decoder and the base64 side. The rest is quite similar. Yeah, and you can imagine how it can be done. Otherwise, you can just ask me a question on Twitter afterwards if we don't get to the questions time. So specifically, I mentioned we're going to look in the web extension crates. So this is a crate that implements event, text encoder, text decoder, file APIs, and a few other things for Dino. We're going to add binary decoder to that. So yeah, binary encoder is done similarly. So you'll see within the lib.rs of the web extension crate, it has an init function, and that's actually invoked during the runtime build and snapshot process that we mentioned before. If you go, we're actually building the extension here, so we can specify all the JS files that need to be part of the extension. So they're going to be embedded, and then during the init process, they're actually going to make sure that all the classes in there are declared during the runtime bootstrap process, and that everything's available when we start Dino. So yeah, basically here we just want to add an extra JS file, binary encoding. There's a few others that are for like text encoder, text decoder, and file APIs. Then the next thing that we have in the builder pattern is we have op encoding binary decode. So this is basically a pair that maps the string name of the op to the actual Rust op that we're going to look at in a little bit. And then just some state-specific stuff that's not super important for what we're doing now. It's state for the extension, and then we just build that extension. If we take a look at the Rust decode op, so this will still be in lib.rs, just a bit further down. We just got to define a binary decode options struct. So usually they have a few other things in here, maybe streaming when they add streaming to this API. But for now, we just have an encoding string, and I just left it as a string to be to make it clear when we match against it later. So if we look at the op encoding binary decode, you usually pass state around, but we don't require any. We don't need to interact with this op states at the moment, so we can just leave it as an underscore. I just wanted to leave it here so so that we could see generally what parameters these take. And then input will be a string, so that will be like an example I showed, your base64 string. And then options is we do also pass that from the JS side, and that will give the encoding that we actually want to decode from. So then it will return a result, and the bytes that we get from decoding will create a zero copy buffer from that. You'll see in a bit. So let binary decode options, we're just extracting the encoding from the options struct. And we'll match just against the string. We're going to get base64. We're not going to do hex and base64 URL. They can be done similarly. Then we'll just create a config. So this is from the base64 crate. We're just using the standard character set. And then we'll return our zero copy buffer. And we're going to create that from decode config, passing in our input. All right, now we're on the JS side of things. So if you thought this was only going to be Rust, then I'm very sorry. So yeah, this is the immediately invoked function expression that is in our newly created JS file. So when this gets loaded into the runtime, it will immediately execute and declare our classes and make sure that everything's in the everything's defined for usage when we actually run Dino. So looking at core, Dino.core basically allows us to use the ops that we have defined. So according to that op pair, so we'll have that string name, and that's how we can basically invoke that Rust op that we looked at earlier. WebIDL I'll get to in a moment. It's from the spec side of things. It's used for basically describing the interfaces that have to do with binary decoder in our case. And yeah, it's just to make implementing things easier from the spec. And it is a web standard now, so it's pretty cool. And then we have Uint 8 array and type error. We import this from primordials, and Node has something similar. This is just like the untampered, pristine classes and things in the global context that we don't want. We don't want to take one that maybe a user has tampered with down the line. So yeah, this is our pristine pool of things to use. And then binary decoder, we're going to take a closer look at soon. And then we've got this web IDL configure prototype. And basically what it does is it sets the relevant descriptors for the prototype of the binary decoder, but it's not super important, so don't stress too much about it. And then we basically we add a binary decoder to our binary encoding property on Bootstrap so that we can load it in the main.js file later. So just maybe a quick overview of what web IDL looks like. It's not important, but I thought it would be a little interesting. So this is what you would normally see on a spec that's defining stuff to be implemented in ECMAScript, and exposed here. We'll say, okay, we want binary decoder to be exposed on in window and workers. So yeah, you've got the interface there, the constructor. It must take a binary encoding. So binary encoding, how it was defined by Luca was just that it's an enum. It can either be like the string hex or base 64 or base 64 URL. So we need that parameter is required. And then we have a read-only attribute that's just set to that encoding. So if we construct it properly, then that value will basically equal what we passed in. And then we have a single method just called decode. We take in an input, which is a DOM string, and we basically return a Uint 8 array out of that. And web IDL itself, IDL stands for Interface Description Language. So yeah, it specifies how ECMAScript should bind to web APIs. Yeah, so next, take a look at the JS constructor. So we can even refer back to that IDL to see what's going on. But we have the binary decoder class. So this is in that same JS file we created, binary encoding. And then we have a private property. So you see the prefixed hash. It's relatively recent in JavaScript. It means so it can only be accessed within the class. We've got our constructor, which we pass an encoding string to. And then we have this prefix for errors that can happen during construction that you normally see, like if you try, maybe you pass like the wrong argument through, and then you'll get an error, like a failed to construct error. And then it will mention what it failed to construct, in this case, binary decoder. We use another web IDL helper, required argument. So this will assert that we are getting at least one argument. And then if not, then it will error out with the prefix failed to construct binary decoder and mention that you didn't give enough arguments or something like that. And then we have, we set encoding. We need to convert that to a DOM string in this case. That's basically just a spec compliance thing. Not going to go into it too much, but yeah, you can also get errors from that. We'll also have the same prefix. And if we look here, so this is just really a simple way of doing it. But I just said if we don't have one of these encodings passed through, so say someone passes like base 32 encoding, but we're not handling it, then we'll basically throw a type error. We'll say the encoding provided, and we'll mention what encoding they provided is not supported. So yeah, so that will also mean a failure to construct. And then we'll set that private property to encoding because we know, okay, it's good. We can construct this. And then we get this little thing called WebIDL brand. So that's like a symbol just to make sure that we're dealing with the correct prototype later. All right, and so now we're going to look at the decode method in binary encoding. So a bit further down, we've got decode. We pass an input like a base 64 string. This is where we use the assert branded to make sure that this, which is an instance of binary decoder, is an instance of prototype, and that it has the right WebIDL brand symbol. Not super important for this talk. Const prefix. So similar to the constructor, we'll say failed to execute decode on binary decoder if we have any like errors in the WebIDL helpers. Also got another required argument. So if we don't have enough arguments, also throw. And then input, we also need to just do that conversion and make sure that everything's okay. But this is the main part of this method. And this is where all the magic happens, is we use Dino.core to the method upsync. So sync means synchronous. So we're not returning a promise or anything from here. It's going to happen synchronously as defined in the spec in Luca's spec. So yeah, we pass the string name for this up encoding binary decode. We pass the input. So that's the base 64 string that maybe we want to decode. In this case, it's still general. And then we pass the decode options object, which would be the struct on Rust side. And this basically is just the encoding that we constructed the binary decoder with. All right, and then we basically add to the global scope of the runtime. So within runtime.js main.js, we have window or worker global scope, because in the IDL we mentioned it needs to be in the window and worker global scope. We have binary decoder, and we make that property not enumerable, and we pass that from the bootstrap object, binary encoding.binary decoder. And then if we've done all that and we rebuild Dino, so I just did a release build to get an optimized build, then what we get is we can use our new binary decoder. We can pass in base 64. We can call the decode method on that. So we pass in a base 64 string, and then out we'll get a Uint 8 array. Yeah, and then we've added functionality to Dino that didn't exist before. Some of this example was a bit contrived and maybe not best practices in all areas, but it was just to give you like a good overview of how Dino's JS interacts with Rust, and how we can develop web API functionality in the Rust extension crates. So yeah, we did it. The binary decoder class is now available in the global scope of the Dino runtime, so we can use it like any other native API. And we also implemented the decode method on the binary decoder class. The decode method calls the op encoding binary decode op, which we implemented in Rust. And binary encoder would be done in a similar way. Yeah, that's all from me. Thanks for listening.
Thanks, Duncan. I didn't realize there was going to be that much JavaScript and Rust in the same talk.
Oh yeah.
So this is actually quite cool for an interop to see the interoperability.
Yeah, I should have given a bit of a warning. It's a lot of code snippets.
No, it's fine. It's just like, I mean, for some of us, I break out in Hive sometimes if I see JavaScript. But this is actually what's interesting here, is to see how you can interrupt the two. So now I'm going to have a look and see if I can spot any questions. I don't see any particular questions in the stream, in the chat stream. I'll give everybody a few seconds. If you've got a question or two for Duncan, you can put that in the stream. And in the meantime, let's see. I'm going to take your slides off, Duncan, and then I can see if I can add Senyo to the screen. You can unmute Senyo and we can check.
Cool.
Hey, so now it's all three of us here. We'll just give a few more minutes, but in the meantime, super welcome, Senyo. I have to go and look at my notes again to see what your talk title is. I don't think we're seeing any questions for that. Do you have a question for Duncan, Senyo?
No, unfortunately not.
Too much JS stuff.
Yeah, I don't know about JS.
No about JS. Okay, cool. There might be some more questions later, Duncan. I'll call you back on stage if I need to. Okay.
Thank you.
So I'm going to just add the title slide again here. So after Duncan now, we have Senyo. Senyo Simpson is working at Aerobotics. I've never met Senyo because we live in a virtual world. I've only spoken to Senyo on ZA Tech and on Twitter, but you're most welcome, Senyo. And Senyo is going to give us a primer on asynchronous programming in Rust. Now, this is particularly interesting for me because I know how to do async programming in Kotlin, so I can do a good comparison.
Cool.
I'm going to remove my slides from stage, and then I'm going to see, have you got your slides up and ready? We can add that to the stream.
Sweet.
Okay, we can see your slides, we can hear you, and with that, I'll leave the stage to you.
Awesome. Cool. What's up, everybody? So my talk is on asynchronous programming in Rust. It's kind of like an intro to async programming plus how it's done in Rust, and then a bit of like a deep dive into how it's all put together, since it's a bit interesting in comparison, I guess, to other languages. Cool, yeah, so I hope you enjoy. So starting off, what is asynchronous programming? Asynchronous programming is a programming paradigm that enables concurrency, where we kind of define concurrency as the ability for multiple tasks to execute at once. So the one good example I saw to explain that is like if you're cooking like pasta or like making a pasta dish, like you'll have your pasta cooking on one side, and then you'll also probably be like making the sauce at the same time, and then like grating the cheese also or something. And like all of those tasks are basically happening all at once. If they were like run in sequence, then you would have to do like make the pasta first, then after that make the sauce, then after that grate your cheese. But obviously you can like kind of chop and change as you go along, and so that's kind of like the paradigm. So got this like quick present like visual for that. So on the right here we have a task A and B, and then on the left we have like how it's executed. And so for task A, the blue sections are where it's executing, and for task B, the green. And then you have this like yield point over here, and the yield point is basically like a quick one. So a lot of async programming uses this idea of cooperative scheduling, which basically just means that the tasks yield the CPU and say like, I'm blocked or I'm waiting for other work or another resource. And so you can schedule another task. So it kind of works on this good faith model. So let's say task A was CPU bound, then I never released the CPU, no other tasks would be able to run. So you have to have these like, it's kind of like a constraint of the paradigm. So yeah, on the left here, we see like task A runs, then it yields, then task B runs after that, and then it yields. In this case, you like there's a dead time because you don't have like multiple tasks, but you can imagine if you had like C, D, E, F, and G or whatever, they would all be put here. And then we have task A getting scheduled again because it's ready before task B, and then task B finishes. So it's kind of like, and all this happens on one thread. And so you can, kind of see like how, I guess, async kind of like works from a visual point of view. Cool. And so, yeah, like every paradigm, it's useful under a set of constraints. So in this case, one is having a large number of independent tasks. So obviously, if you have dependent tasks, that would make them sequential. So in this case, you have to have independent tasks, and that they are IO bound. So that means execution time is dominated by the amount of time they spend waiting. And so during this waiting, other tasks can be scheduled. And so, if you're CPU bound, then the CPU would be used all the time. So one of the obviously constraints is that a lot of the execution time is spent waiting, where I can schedule other tasks while another one is waiting. Cool. And so just to read this paragraph, so these type of workloads are fairly common. The most common of them being web servers, which most of us interact with fairly often, or build fairly often. And yeah, so because microservice architectures are becoming like the de facto architecture for software building, it's no surprise that async programming is like garnering all the attention it does, as well as like on mobiles also, it's also utilized. And so, yeah, this is what makes it important. It allows developers to create highly scalable web systems or just software systems in general. And so, like per microservice, like a replica, you can do quite a substantial amount of work. So, yeah, so one question I'm sure that you're asking, maybe not, is surely we've had concurrency primitives before. So what makes async so special? This is a great question. And so one of them is that, or one of the ones that makes it particularly special is that we can write code that's almost equivalent to synchronous code, yet still benefits from all the goodiness of asynchronous code. So, like in most languages, you kind of have these two keywords, async and await. In Golang, it's just like go. And so those is basically all you need to use to basically convert synchronous code to asynchronous code. And so funnily enough, I have an example in JavaScript, so back to JavaScript land. And you can see here, we have this function login. And then we've got this like async keyword here. And then we've also got, these awaits here. And this is basically all that's needed to make a like async function. Obviously, like internally, they actually have to be async, like the functions themselves. But it's very close to synchronous code. So there's not this like huge shift in paradigm when you want to write asynchronous versus synchronous, which I believe there was before. I don't have much experience with like writing callback-based asynchronous code, but that was the paradigm that kind of like predated this. And it had its own set of issues and usability or UX issues. And so, this kind of like a step forward for writing async programs. Cool. So yeah, no more JavaScript. No one came here to do JavaScript. So how Rust does async programming. So the meat of the presentation. So let's first chat about some constraints particular to Rust. So firstly, Rust has no runtime, and it wants to stay this way. And by runtime, you can really just think about garbage collector. Rust doesn't have a garbage collector. And that's because it's a systems programming language. So garbage collectors can impose performance overheads that are one, possibly unpredictable, and two, they just like, it has a performance overhead by its nature. And so it's something that Rust doesn't want to have because of the focus it has as a systems programming language, and working in places where like C and C++ would work, which also have no garbage collectors. And so fun fact, actually Rust used to have one, but they took it out because it adds performance costs all around. So Rust is committed to zero cost abstractions. That's number two. That means that what you don't use, you don't pay for in performance. And that's actually why they took the runtime out. So the runtime imposed like global costs on Rust, meaning that whether you used in this case, it was for like adding user level threads, whether you use them or not, your performance was impacted, and so they took it out. And so yeah, they committed to zero cost abstractions. And a nice guarantee, or like one of the things they try and guarantee with zero cost abstractions, is that if you use them, you couldn't make the same thing better yourself. So you don't pay for performance overhead, and they put like the best implementation possible, basically. And then yeah, given those two things, async support must not induce any additional overhead if it's not used. So these constraints have significantly shaped the design of async programming in Rust, which is, I guess, why this talk is even relevant. And so async primitives are zero cost, obviously, otherwise, would have already failed on one of our constraints. And to execute asynchronous code, you need to use a runtime. These are external libraries provided by the ecosystem. So 2 leading ones are Tokyo and Async Standard. And so the nice thing in this case is obviously if you don't need to write asynchronous code, you don't pay performance costs. But once you do, you add in the runtime. And then the runtime being the thing that like executes all of your asynchronous code and does all the management of it and all that. So yeah, once you add it in, then you obviously pay the cost, but you know it still allows you to choose depending on what your needs are. And then they've had to use lazy computation in order to ensure that zero cost is adhered to. So that we'll get to later. Cool. So yeah, let's see some async Rust. Cool. So this is this Tokyo thing that I was talking about. It's just the library. And so we can write this code. And so I should have actually just cleared this up, but let's actually change this to like 10. And then if you run that, hopefully we'll get 10 out. Otherwise, don't do live programming. Let's see what happens. Well, that sucks. There we go, 10. I was just taking note. Cool, and then we can possibly change that to whatever, 13, 14, but I don't want to wait again. So, yeah, so we have this async Rust, and like that's basically like a quick example. Those are rather uneventful. And so, yeah, let's take a peek behind the curtain. I'm sure that you'll find that way more interesting. Also to note, like it looks similar to a lot of other languages, so like nothing too crazy. In this case, like await is like a postfix instead of a prefix, but you know, otherwise pretty much the same. Cool. So let's start off with futures, which is kind of like a basic building block of async. So what in the world are futures? A future represents a computation that will complete in the future. And by that, what we really mean is like, you know, if I schedule a task, I can tell the CPU, like, listen, here's some work to do. I'm not interested in it right now, but I'll come back to you later and hopefully it'll be complete, right? And so the future represents that computation that like it would be finished in future, but not right now. So there are units of work that get executed concurrently, and we've already seen one. So this is actually a feature, just like future like that. So we can run that. Cool. So that's basically a feature. This thing actually like implements some interface. So like the type you'll have will be something like output equals 32. But not entirely that important. All this to mean that this thing is something that implements future, and it is a feature effectively. Cool. So in Rust, features implement this feature trait. A trait can be thought of like an interface or like an abstract base class. I think that's the right term. And so, yeah, this feature trait or interface is this. The only thing that's really important for us to note here is that there's this poll method, which we'll talk about subsequent slides. So yeah, this feature trait has this one method poll, and this is where it gets all interesting. So buckle in. Cool. So in Rust, features are lazy, similar to like Python generators, for instance, they're also lazy. And so basically this means that nothing happens when you create them. So you have this example. And so you'll see here, let's see, that we have this like future, which has async 20 in it. And when we run it, nothing happens. Cool. And then instead, like if we do run it like this, and then we call like future, and then we await that future. So yeah, if we await that future, then when you await this, then it begins processing in the background, and then you know it actually resolves to some value. So if you run that, hopefully you get out an answer. So you get 20, right? So when we create a future, it's lazy, which means that we can create as many of them as we want to, and literally nothing will happen. And that's how it ends up being zero cost, because there's no like additional work that happens when futures are created. But then once we add in the runtime and then we await them, then they get evaluated, and then like the work gets done. Cool. So this is where that poll method from the feature trait or feature interface comes in. And behind the scenes, poll is called when we await a feature. And so when a feature is polled, it makes as much progress as it can, and then that'll either complete or have to wait for other IO resources. So like a really stupid example I was thinking of before this talk is kind of like, let's say you wanted to get like from place A to B, and I only gave you like a limited amount of like petrol. What would happen is like, you know, you'd have some petrol, and then I would say like poll, and then you would put your foot on the accelerator and then like drive until you run out of petrol. And then now you'd be in this like waiting for other resources state, which is more petrol. Then, you know, somewhere along the line, someone gives you more petrol, and then you can drive again. And then at some point, you'll get to your destination. And so that's kind of like the same process where we have this runtime, which we'll call poll. The future will do as much work as possible, and then either it'll complete, so you get to your destination, or you'll have to wait for other IO resources, in the sense like wait for petrol. So yeah, and then this call to poll returns a poll object, which is defined as ready or pending. And so if it's ready, that means it's complete. If it's pending, that means that we still need to do some more work, and we're waiting for other resources, and then you can schedule us later to do some extra work, basically. So yeah, as I've said, if it's unable to complete, it returns poll pending, and then if it is ready to complete, then it will return poll ready T, where T is at the top of the output, basically, nothing too crazy. And so if you kind of think of like a real world example of this, or like real world in terms of computing, a good one could be like waiting on a socket. Let's say you have a TCP connection to your socket, and you're waiting for data to come into a buffer. And so like data will come into the buffer, and then you'll read it. And then if you're still waiting for more data, then you would return poll pending, because like I'm still waiting for more data. Then more data arrives at the socket, you read it again. And then once you've read all the data that you expected to read, then you'll say like, cool, I'm ready. I've finished all the work I've done. This should be over here. Cool. So yeah, that's basically that. And so we can actually easily create our own feature, which is pretty rad. And so this struct basically creates this feature, and all it does is this thing holds like a value, like an unsigned int. And then we have this poll method, which we implement ourselves. The only thing to like note here is that we print some message like, okay, cool, we're getting polled. And then we return ready immediately. So we don't append in this case, which just basically means like the future is always, that's why it's called ready feature. It's always ready. And it returns the value that we specify, or the integer that we specify on initialization. Cool. So you can run that. And then here you can obviously see an output already, but like, let me try and change that. Let's see. So yeah, you can see that that poll method got invoked. So this here prints, and we get out an output. And then we can also see that action of the lazy feature. So you can see here, if we do nothing, then we get nothing out. And then once we await that feature, then we get the output that we expect. Right? Cool. So that's kind of like, I guess, the basic like features and the kind of like basic building blocks. So we know a couple of cool things now. One, features in Rust implement this feature trait, or like interface, if you can think about it like that. These have a poll method, which is used to advance the feature, so make as much progress as possible. If a feature finishes, it returns poll ready. Otherwise, it returns poll pending. And features are lazy. Nothing happens if you don't poll them. And so I think the laziness part is kind of like the big part that's different from other languages, in the sense that they kind of like automatically run them and invoke them for you. Whereas in Rust, you have to create them and then go through a process of like actually driving them to completion manually. Like it's all handled by the runtime, but I mean, runtimes have to do that work. So yeah, still it'll be better if I could see how everything's put together. I'm glad that you think so. So let's create our own executor. So before we were using Tokyo to do all of that stuff. So now we're just going to walk through the process of creating our own. There's a bunch of code in here. A lot of it's not necessary, but I'll talk you through the parts that are important. Cool. So we're going to write a super simple executor. It's taken from like a tutorial from Tokyo. If you want to check it out, so you can just go to their website, click on learn, and then go to like the async in-depth section, and you'll find it. Cool, I already ran that. Cool. So a task is kind of like the unit of work that we need to run. You don't have to worry about the types. Honestly, I don't even understand some of them. Like, what is this? I'm just joking. Cool. So a task has a future, which is something that basically over here, all this really means is that it's something that implements this future trait that we talked about earlier. And then it has this sender, which is just the send side of like a channel, and basically all this thing is responsible for sending the task to the executor. So it'll come together over time. And so, well, I think I might need to zoom out here a little bit. Cool. So here we have a task. The most important thing is this poll method and the spawn. So for the poll method, this is basically it's used to poll the task, which internally polls the feature. And so all that really means here is that we have this feature that's connected to our task, because it's like a field on our task. And then we take that feature and then we pull that feature. So this will basically be responsible for driving that to completion in essence. And then we have this spawn method, and all this does is takes in a feature and then creates a task. So you can see here we've got like a new task being created, which has a feature, and then this sender, which basically sends this task to the executor. And then when we spawn a new task, we automatically send it to the executor, like on initialization, basically. And I think this code at the bottom, yeah, we don't need to worry about that. So yeah, a task basically is this thing that holds a feature and basically can send itself to the executor to be executed. Right, and now we have the executor, and so I think it's changed my one, yeah. And so this executor has a task queue. Basically, in this case, it's a channel that receives tasks on, but you can basically think about it like as a vector, you know, that just backlogs tasks as they come in. And so yeah, it holds all the tasks that we need to run. And then this sends tasks to the executor. We only attach it to the executor like structure or whatever, because we use it when we initialize tasks, or when we spawn tasks, basically, which again will come together. So we have this new function which basically creates the executor. So you can see here, this creates our channel, and then we've got the sender and the task queue. And then this is, I guess, the most important part, which runs the feature. And so you'll basically see we receive, this is a blocking call, and basically we receive tasks off the queue. And then we call like that task.poll, which will internally poll like the feature that's attached to the task, basically. And then this method is just used to spawn tasks onto the executor, which calls tasks spawn method. And so effectively what this will do is create a new task with that feature and then send itself to the executor. So that's that. I think we're actually almost done, right? Then this this is pretty short. It's just it's a feature that we're implementing. So this is a delay. And in essence, all this does is waits a period of time. So what will happen is if we set a delay for 5 seconds, it will basically return poll pending. And then after 5 seconds, it will return poll ready. How that's implemented is like out of the scope of the store, but nonetheless, that's what happens. Cool. So what we'd expect to see is this like pending get printed, and then this we are ready, like when it's ready to run. I think I forgot to actually run this. And we can make this like cool. And so if we run this, we should get that hopefully. Let's see. We got pending, and then we wait some period of time, and then we're ready, and then start. So that's basically that. This thing will never stop executing because it's always waiting for extra tasks. but yeah, that's basically the whole talk. And so yeah, in essence, for an executor, we have these constructs, the task and the executor, and all we do is we set up a task which holds a future. We poll that future, so we spawn that future here, which will then create a future and send to the executor, and then we call this executor.run, which will wait on the queue and like execute tasks as they come in. And that is everything.
Great. I'm going to leave your slides up for a second because we have some questions. Duncan wants to know, do you prefer Tokyo over Async STD?
I haven't used them too much, so I wouldn't say I have a huge preference, but Tokyo seems to have most of the momentum behind it, and there's a kind of like a whole ecosystem built around it. So I tend to just use it purely because like I feel like the most popular out of the two. Yeah.
Okay. And the name's more easier to pronounce as well.
Yeah.
And then I have a question. I wanted to know, what's the debug environment like? I'm just going to take, do you want to show us more slides or show us more anything? Because I can take your slides off.
Yeah, you can take them off. You can take them off.
Okay, cool. So I wanted to know what the debug environment was and if there were tools or testing tools to help either debug or test these async things, because they're typically tricky to debug and test.
Yeah, so as far as I know, not that much, but there is a lot of work going on with that at the moment. And so they have this idea, like Tokyo is working on this thing called like Tokyo Console, which is kind of like top for like tasks that you're running. And so that'll kind of like output like, you know, what tasks are in progress, how long they've been taking to run, all that stuff. And so that's kind of like a diagnostic tooling that I know is busy being made. But in general, I don't know too much about that, if it is a huge thing yet or not. Yeah.
Duncan's on stage with us. So, yeah, I was just hoping that there would be like some help to stop you from, if you like, you know, if you make a deadlock or you make,
yeah. So like with Tokyo, for instance, they have implemented this idea that like each task sort of like has a budget. So you can't actually spawn a task and it will just block everything else. If it's been running for too long, they'll just like take it off the CPU and run something else, which is just kind of like an optimization they've decided to make, which I guess makes sense.
Yeah, it makes it much safer. And then, I had another question. In Kotlin, you've got this concept with the coroutines, and I think in Go as well, where you're not actually managing the threads yourself. This runtime that you were speaking about actually does the threading. But in Kotlin, you can tell it, okay, I wanted to use like the environment or the scope, which has 1 thread or 2 threads or 3 threads or whatever. You can control that. Do you have that kind of control in your runtime, or?
I'm not sure about the number of threads. I feel like yes, though I'm not entirely sure. But you can also choose. I know that you can choose between single and multi-threaded executors. I'm not sure if you can specify like the number of threads or environments, but I feel like that is definitely possible. Like it should.
Yeah, because I think typically what you would use that for is like, say you had something that's very IO, you could have one of these executors that work just for IO stuff. And if you had something else that needed to do a lot of computations, you could have another one. And then the two wouldn't fight about the about the resources. Let's just see if there's any more questions. I don't see. Lots of people are saying great talks, great talks. Let me put those on the stage for you so you can see those. And then while you read those, I have some questions that I want to ask. So I'm just getting some good feedback for you. Okay.
Cool.
Aha, Ewald says, out of interest, has using Rust changed your general approach to software development in any way?
So for me, yes. And mainly, I guess for me, the biggest thing has been on error handling. So Rust has this idea, and I think it's standard in like all the ML programming languages, that you have like an option type or the result type, basically. And so it encodes in the type system that like something can fail automatically. Like if you have a result type, you get either the type encodes like fail or some type like integer or whatever that you get back. And then the option type will be either none or some value. But because they've got different names, like an option is basically a none or something, you have to handle the case where you get like none out. And so for me, that's kind of like translated into being thoughtful about like how I write, let's say like Python, where, you know, in Python you can return none or an integer or a dictionary or whatever at different points in your program, and like someone just has to cater for it. And so for me, it's being like way more thoughtful about, you know, like if my function can fail or will return a none, like how do I communicate that properly, or do I return like a tuple or something that has like whatever. And so that's basically been, I guess, like the most biggest change for me. Outside of that, there are just some stuff, like I guess you learn a lot about, like, Rust doesn't hide too much from you, so you'll start learning about like all the low level stuff, and that does kind of like frame the way you think about things. But I mean, you don't have to think about it too much.
And you, Duncan, have you got any changes that you noticed in your coding behavior from using Rust?
So yeah, I also think like using Rust, I come primarily from dynamically typed language background, and you know, everything like that. And you know, I came to sort of appreciate a strongly typed language, and sort of also I work every day with TypeScript, and I know that's a layer over JavaScript, and at the end of the day you're dealing with sort of dynamic typing in the runtime. But yeah, I think some of my approaches in TypeScript have changed just from using Rust. Is also around making sure that you check everything and your type safety and things like that. But I want to say, like, if I'm just using Rust, it's sort of like the one major thing that I love about it is I've never had such helpful compiler errors in my life.
Yeah.
It's almost like compiler-driven development.
Oh, that's super interesting. So if you say it's got strong typing, does it have a nullable? Have you got this concept of nullable or non-nullable types? Because like Kotlin, you can have a string or a nullable string.
So there's no... Yeah, Duncan, you can go.
No, go for it.
Oh yeah, saying so in Rust that would be like an option type, and an option would be like an option encodes that this thing can be a string or none, but then you have to handle the case where it's none. So that's basically how it's encoded in Rust. Yeah.
Oh, okay, so it's like a none. Okay, so my next question to both of you is, what's your favorite feature in Rust that you don't see in other languages? And on the flip side, what's a really nice feature in another language that you like, but that you wish that they had in Rust? Let's see, Duncan can go first.
That's so interesting.
Me going first. Okay, I'm actually going to turn the question around. I'll first say something that I kind of miss in Rust, but have sort of not... like I've not missed it that much recently, is around actual optional parameters. Like, so it's like I've gotten quite used to the boulder pattern in a lot of my projects, where, like we saw in Dino as well, like where you build the extension out, use methods to, you know, tack onto that struct, and and then end it with a bolt. So I still do use a lot of optional parameters in TypeScript and that kind of thing. So when I go to Rust, it's sometimes a bit of a, but there's, like, I don't miss it as much. I feel like, you know, idiomatic Rust gets around it okay.
So are you saying that's where if you've got a function with 4 parameters, that you only need to put in 2 of the 4? Is that what you mean by optional parameters?
Yeah.
Okay, so in Kotlin you can make default values, so that would make them look like optional. I mean, I'm not sure what happens in JavaScript, but then in Rust you're saying you can't do that. Do you have named parameters in Rust?
So is it like labeled parameters?
Yeah, so you can say this parameter, and give them the name so that you can get them out of order if you need to.
No.
Oh, I think I'd missed that. I'd missed that. And you, Senja, what features do you miss and what features do you love?
So yeah, the optional Once is a big one for me, and I think also like having default values. Like sometimes you just want to be like the default value is 5, just make it 5, but there's no such thing. And so, but it doesn't feel that bad. But I guess like it's definitely something I miss. And then my favorite feature has to be pattern matching. I miss that like all the time when I'm writing Python. It's just so convenient. And so that's definitely the biggest one.
Did you say your favorite feature, Duncan?
Oh no, I didn't. So there's quite a few actually. I think of one.
You can have 2 or 3. Okay, you can have 3.
No. I'd say I also really like the pattern matching, to be honest. It's extremely powerful, like things that you thought it might not be able to do, like sort of surprises me every day.
For sure.
So it's really cool.
Okay, so my next question is, Rust is sort of touted as like the C replacement. So what areas, where do you think we'll see people using Rust?
So Rust at the moment is basically used in like anywhere where you need, I guess like anywhere where you need C or C++ in the sense that like you want very high performing software. So you can imagine things like databases, in-memory databases, like TCP stacks, like all your networking stuff, like that kind of spaces where it's primed for. But I have been seeing a lot of people like trying to like using it for standard web development, or like cloud native web development. And a big reason why people enjoy it in that space is because it doesn't have a runtime. It has very predictable performance. So like if you read enough around, you'll often find that companies at some certain scale, they'll start having problems with their garbage collector. And so like it'll start collecting garbage, and then your latencies will skyrocket for like that period of time. And so with Rust, you don't have that. So you can pretty much say like my latency is constant all the time. Obviously, there's definitely probably like exceptions to that rule, but that's the one case where people are kind of like justifying it for using like in standard web dev. So yeah.
I can also mention somewhere where I've seen it being used more and more is, coming from Luna, more exposed to a lot of the open source Bitcoin projects. So if we just look at Bitcoin Core, like that started in 2008 roundabout, and it was in C++. It's still in C++ today, and but a lot of these auxiliary projects starting out maybe in the last 2 or 3 years have actually started in Rust, and the like number of contributors that join those projects, it's also like systems level stuff, and distributed systems, things like some lightning kits, things like that. I think the barrier to entry is much lower for systems language like Rust compared to C++, and everything seems familiar. At least that's how I experienced it when switching between projects and things. And
okay, I see there's another question in chat. So chat wants to know, and Nelly wants to know, pattern matching as in regex. So I think maybe give us an example of the kind of pattern matching that you would do in Rust.
Sure. So it's more, I guess, how do you even describe pattern matching? It's more that you match on like, I think in this case, it'd be like structural pattern matching. So you'd match on, let's say you have a tuple that returns like an X and Y coordinate or something. Then you can like destructure them by creating it like, let me see if I can pull up an example. That would just be way easier.
Okay.
Yeah.
Let's see if I can. So while you're thinking about that, while you're pulling up an example, I'll put your screen up and just see if I've got another question. So you were saying about that there's no garbage collector. Yes. But now I was thinking about that, right? So can you do like memory allocations?
Yeah, of course. No, definitely.
And then then you have to remember to free, or how are you doing that?
So that's like part of Rust's types, like not in type system in terms of like the way it's implemented. So Rust uses, I think, something called reference counting, basically.
Oh, okay.
And so basically, like when it drops out of scope, it'll just free the memory for you. And so
okay. So it's got like a reference counter thing that's happening in the background. So I'm assuming that's at compile time, right? So it wouldn't be at runtime.
Yeah, as far as I know, mostly, as far as I know, yeah. But there is there is technically a runtime. It's just like so lightweight that it's effectively not a runtime.
Okay.
Let me see if I can share my screen here. Let's see.
Okay, I'm going to hide Anila's question.
Cool.
Fritz says it's a switch statement on steroids.
Effectively, that is true. So you can see. Can you see is my screen on?
Wait, I'm going to add your screen.
Okay, cool.
Yeah.
So
you can see him.
Cool. So you can see here you have this like let x equal 1, and then you can match on x in this case. So I guess you get like there's something called structural pattern matching, and then I don't know what the other one is, but this doesn't feel like structural pattern matching. And so in this case, this would just match on like what is contained in this variable. So this would get printed in this case. And if you change this to 2, this would get printed. And then if it was like 5, then this would evaluate. This is like a wild card for like if it doesn't match any of these. Do this.
I see. So it's, I mean, if you had to code that normally, you would have like if and else statements, right?
Yeah.
You'd have like a whole nested if else statements. Okay, yeah. So Kotlin has a when statement that does something similar.
Okay, cool.
Okay, cool.
And then you also get these kinds of pattern matching. So this is like a structural pattern match where you have like x equals sum 5, where if just for the sake of saying sum is like sum struct, if you wanted to say that. And so when you match on x, it will compare these branches. So here in this first one, sum 50 doesn't match because this is sum 5, but this sum y will actually match. And the reason why is because this is basically binds to this variable in here. And so what will end up happening is this will run and print out, this will run here and say matched y something.
Okay.
And so you can also kind of think about this like if you had to destructure a variable, like you could say like let sum y, like let this equal sum 5, and then y would automatically equal 5. That's basically like a type of pattern matching. And so yeah, it's just goes to this.
Sure, it's amazing. Yeah, you can see you can do actually pretty cool stuff. I can see that you'd miss that if you don't have it right, because you'd have to write.
Yeah, of course.
Yeah,
a lot of it. So like here's a good one on the like pattern matching. So you've got this point which has like an x is 0 and y equals 7, and then you can match on that like variable, I guess, where here you've got x is an a and y is equal to some b, and this a and b will bind to 0 and 7 respectively. So these things, now a is equal to 0 and b is equal to 7 because of the way this thing is destructured. So that's also a type of pattern match. So that's basically one of the things like, I miss it all the time.
Okay.
Match like beautiful reference things and do some funky stuff with it too.
Yeah.
Interesting.
Okay, so then my next question is, what's the IDE environment? What's the dev environment like? What do you use?
I use VS Code, and there's like a LSP called Rust Analyzer. So I use that. I think there's also Rust IntelliJ or something. I don't know.
Is there an IntelliJ version for Rust?
Yeah, I think there's
Yeah. Okay.
Yeah.
Cool. Okay, but I guess if people that come from the web world also like VS Code, and I think so VS Code. So then I'm assuming you can do like breakpoints and debug inside there. It'll all be integrated.
Mm-hmm.
And then the last question is, will your slides be available, and/or what are your favorite learning resources for learning Rust if someone wants to learn Rust?
Duncan, you can go first.
Okay, cool. I will make my slides available. I just they're not prepped. I need to just convert to PDF or something. And then also use VS Code with Rust Analyzer. It's really good. And then the last part of that question, what was it again?
It's the one about what are your favorite learning resources? If I want to start learning Rust, where should I start? What are some good links? We'll put the links in the description, and we'll put the links in our tweets as well.
Yeah, so you definitely should start with the Rust book. It's just so good.
100%.
Yeah.
The Rust book. Okay.
Yeah, I'll show you if you just type it, but maybe let me just share. Can you share it, Maya?
Yes, I'm looking to see. Did you put your screen up? You sharing your screen?
No. I just shared the link.
Oh, you shared the link to me.
Yeah, to you.
Okay. All right. Let me see if I can share. Okay. Let me see if I can share. We have the technology. I can share. Oh no, do we want to share the screen for the Rust book, or are we just going to share the?
Let me share my screen actually. Then you can also.
Okay, I'll put that in the comments as well. We'll put that link in the comments.
This is not right. So I clicked the wrong things. Let's just share.
My keyboard's not working. My remote keyboard's not working from the load shedding. Okay, so that's the link.
Let me just make Docker.
Okay, Docker, add to stream. Okay.
Everyone's eyes. Okay, yeah. So this is the Rust book. If you just type Rust book into Google, it should also get you here. It's doc.rust-lang.org/book, and this is really, it takes you from real basics, installation, programming and guessing game, really getting to know the Rust primitives and things. And I think you end off like implementing a web server, right? Something like that. But yeah, it's sort of nice. It's a great reference. Like I even go back to this, to check things that I might have forgotten, or definitely. And then I think the sort of auxiliary to this is Rust by example. So that's always quite nice if you're looking for a specific thing, like a specific idiomatic example of something. And then I can also chat about more intermediate level stuff, because I feel like that's where a lot of people maybe they seem to drop off, and they feel like, I can't find any content. And I think that's where streams really become helpful. There's a lot of streamers that maybe I can share the links to on Twitter.
On Twitch, you mean? Twitch streamers?
Yeah, Twitch streamers. And then also there's a recent book, Rust Forestations, by one of these Twitch streamers, and it's sort of aimed at the intermediate to more advanced Rust. So I think, that you'll probably start, seeing less resources when you become more intermediate, and you've got to dig a bit deeper and maybe read source code, that kind of thing. I don't know, if you've got any other resources.
No, not particularly. There's a person named John Jengist or Yengist, I'm not too sure. He's the one that wrote Rust Forestations. Yeah. So he's pretty good. But otherwise, the book, like, that's how I started. I'd highly recommend it. It's pretty much.
Okay. So for the audience, we're gonna put all of the links. We'll collect the links of the slides and the resources and put them in the thing. I don't know if anybody else has any more questions. You guys don't have questions for each other. And with that, I'm going to say thank you so much. This has been super interesting. Thank you very much for prepping and for doing a talk for us. And also, again, a little plug for Peach Payments, who is our sponsor. So thank you, Peach Payments. Let's see if there's anything in chat. Borrow checker. Can you guys comment? Okay, we're going to have this one. All right. No, you can't go yet. You have to talk about the borrow checker. Go.
I feel like I haven't encountered the borrow checker. No, I have. No, I actually haven't. I don't know. It gets to a point where it doesn't really bother you that much.
What is it? I don't even know what it is.
So the borrow checker is basically it checks how many kind of like references or aliases you have to a certain variable, because Rust has a certain set of rules. So you can only hold one mutable reference to a variable at a time, or any number of immutable references. And basically the borrow checker makes sure that rule is enforced. And so what people will often do is have like mutable variables and pass them around, and then the borrow checker will say, listen, you can't actually do this. You can't borrow this thing as mutable. And so that tends to happen a lot. And then there's also, it has like interesting move semantics and stuff like that. So depending on that, you'll always get these errors that crop up and say you can't use this variable here because you moved it somewhere earlier.
Okay, so it's like the Rust Grinch, that like if you're being too loose with all your variables. But I mean, it makes sense. It's mutable variables, right? That could be like a concurrency. There could be a concurrency issue around mutable variables. So it's obviously best to keep things immutable as far as possible, and then just make them immutable when you need to.
Exactly. So that's pretty much it.
Yeah, it's all at compile time as well. So you're trying to compile your program, and then the borrow checker shouts at you, and it's called fighting with the borrow checker. I must say, like, the errors have improved significantly, and the amount of context that the compiler has or like shows you, and it's like it makes suggestions. It's just amazing. Like, I've got to like praise the compiler again. But yeah, it's like, I think when I started as well, it was I mean, I've been on and off with Rust, but I've been playing around for like a few years, and maybe some of the errors weren't as helpful, and you have to dig around and try and find out. And I think those were the days of probably the worst fighting with the borrow checker. Whereas once you get used to it as well, obviously you will encounter it here and there when you're using more complex stuff, but your brain sort of gets into that thinking of how a Rust borrow checker works, and then you get onto lifetimes, and you sort of all over again.
Oh no! Now you have to tell me what that is, because I don't know what that is either.
So lifetimes are basically, so Rust basically computes how long certain variables will live for, and in some cases it can't automatically figure that out, so you have to specify it yourself. Normally, like when you're holding like a reference to something inside like a struct, basically. And so when that happens, then it's like a very difficult thing to wrap your head around, and how Rust enforces those rules and everything like that. So as soon as you start hitting lifetime and specifying them yourself, it becomes like pretty difficult to reason about them. Initially, it definitely gets easier, but I'm still at the it's still difficult to think about them stage.
So I guess by the time you know how to reason about it, then that's when Rust has changed the way you code, right? Because you're just thinking differently, and so all of a sudden it becomes easy.
Possibly, yeah.
Okay, chat. I think, sorry, Duncan, go.
Sorry, Maya. I think one of the ways people in the beginning try and get around, too much lifetime stuff is they'll clone a lot.
Yeah.
It's like, obviously you got that extra cost of doing that, and once you get more advanced, and lifetimes are also introduced in the Rust book, so sort of maybe not in all its gore, but definitely I still refer back to it, because so it always feels like maybe that is one of the things that I would consider as the steep learning curve. Getting to the steep part of Rust is definitely lifetimes. Yeah.
Okay, so that's what our next talk's going to be about, right?
Hopefully we'll get there.
Okay, I think I'm going to let you go.
Cool.
I don't see any more chat questions. Chat people, this is your last chance to ask our fantastic guests questions. I don't see any. I think with that, I'm going to say thank you so much. Thanks to the audience, and thanks to our fantastic speakers and our sponsors. And we hope to see you again.
Thank you.
Bye.